So we have seen what stars do in spiral galaxies, but what about gas? This is a composite picture of a lot of neutral hydrogen images of a lot of different spiral galaxies, and you can see that in many cases you see spiral arms just fine. Well, there are many components to the gas in spiral galaxies. There is cool neutral hydrogen, which we denote as H Roman 1. Then there is molecular gas. Usually most of that is actually molecular hydrogen and then carbon monoxide, but there are hundreds, if not thousands, of other species of molecules out there, some of them very complex. And the importance of the gas is that that's the fuel for star formation. You need to have cold gas, cold interstellar material clouds to collapse and be able to ignite nuclear fusion in core. Now there is ionized gas as well, ionized by the ultraviolet radiation from young stars, and that's what makes those pretty pictures of nebulae in star formation regions. And that we can observe it through optical spectroscopy or other forms of spectroscopy. But the neutral hydrogen is best observed through the spin flip line, which I'll explain in a moment, at the wavelength of 21 centimeters. At that wavelength, radio waves go through the dust, and so we can see all the way through. So just as there are stellar disks, there are gas disks, and they also can show spiral arms. But one important thing is that hydrogen disks extend further than the optical ones, sometimes by a substantial factor. And because this spin flip line is so sharp and well defined, it can be used as an excellent tracer of velocities of gas, including rotation of galaxies due to the Doppler shift. This is how it works. In a hydrogen atom, you have a proton and an electron, and there are two possibilities for their spins to be aligned or anti-aligned. One has a slightly higher energy level than the other, and that transition corresponds to the photons of the wavelength of 21 centimeters. So this is where it comes. Now, this is not something that's easily achieved in the lab, but can happen easily in densities and temperatures of interstellar medium. So there's plenty of it. And this 21 centimeter line has been main tool to probe interstellar material of these galaxies near and far. So here is a contour map of neutral hydrogen superposed on an optical image of this galaxy, and it's obvious that hydrogen goes much further in visible stars. Now, by observing Doppler shifts of the 21 centimeter line, we can see the velocity field, and that looks like this. These are the lines of equal radial velocity, and they'll look like this because on one side the disk is coming towards us, and the other is going away from us. Because the gas goes so much further out than stars, we can measure rotation curves much further using this method than, say, through optical spectroscopy. So here is a simple comparison of optical and hydrogen images of famous spiral galaxy M81 in the Virgo cluster, and you can see that gas is nicely concentrated in spiral arms, which is, of course, where stars are made, although it tends to be a little more extended. So that was the atomic gas. What about molecular gas? Aside from hydrogen molecule, H2, the next most prominent one is carbon monoxide. Incidentally, all of the different molecular species tend to be found in same places by and large. Now, in the case of molecular clouds, which are colder, they get to be closer to the dust lanes, and they're closer to the regions of star formation. You can see spiral arms outlined even better. But there are also new features. There are rings of molecular gas around galaxies. There are bars and other things. As you probably learned in astronomy before, the interstellar medium has multiple phases. I touched upon that a few minutes ago. First, there is a cold interstellar medium, and that's mostly the neutral hydrogen gas. Temperatures ranging from typically tens to 100 degrees Kelvin. So that's all of the cold gas, both atomic and molecular, as well as dust. This is what makes stars in the thin disk of galaxies. Next, there is warm interstellar material, typically temperatures of thousands or to tens of thousands of degrees, and it's warmed up and ionized by the radiation by young stars. And that's where all these pretty nebulae come from. And finally, there is hot interstellar medium, which really mostly belongs to the galactic halo. That's the gas that's expelled from the disk through explosions of supernovae, and the shock waves of supernova remnants are what heats it up to this particular energy. Here is the typical spiral galaxy rotation curve with its decomposition into the bulge, disk, and dark matter components. We spoke about this extensively when we talked about dark matter, so I will not dwell on this much further. And next, we will look at where does the spiral structure come from.